residuals. I'll say more about that in a second. And then there's other things that I don't even put on here, like measuring isotropy, so basically doing a Hubble diagram for lots of different parts of the sky. And when you have 400,000 supernovae, that becomes very possible. And then you can do a bunch of interesting galaxy survey correlations. And there have been kind of new papers detailing about if you have these big galaxy surveys and you have this huge amount of supernovae, how can you correlate them to do something new? All right. Okay, so the other key thing is kind of how people think about Type Ia supernovae is that, oh, well, aren't you just systematic limited anyway? Like, why do you even need to do this? And in truth, basically, we have the same statistical uncertainty as systematic uncertainty, and that has been the case for the last 5 Type Ia supernova cosmology papers. Like, they just keep staying together, and that's not a coincidence because basically we are pushing down systematics as our statistical samples get better, and we're also using our statistics to improve on our systematics. But one of the key problems with Type Ia supernovae is that there's a number of studies about the astrophysics of these supernovae, and then there's kind of the cosmology side, and these really just have drifted apart over the last decade. That if someone said, I know the progenitor system of Type Ia supernovae, I have no idea what to do with that in terms of cosmology. I mean, that's kind of how far apart things have gotten. But I think what's exciting with something like LSST is that these will start to come together, and I think these have to. So what I'm showing here is basically in 2014, this is the Pansar's analysis that I did, and this is just the error budget. And this is now in 2018, this is the error budget. And what we've been saying for the last decade or so is, well, we're just totally dominated by calibration. So we just need to work on calibration. Well, what's happened is that we've worked on calibration, and we've been pushing down the calibration uncertainties. And I think we've kind of been a bit more realistic about kind of more the supernova physics uncertainties. So what you should see here is that basically what systematics of the intrinsic scatter, how kind of different supernovae are one to another, or what is reddening with regards to Type Ia supernovae, they are as big as calibration, if not a little bit bigger. So you push down calibration enough to the point that we finally actually really have to understand the physics again. And that's kind of the next big obstacle. Well, what's exciting about that is that with LSST, you can start breaking things into different samples. So this is I think one of the most confusing things right now in Type Ia supernovae, which is that if you do all your standardization, you put everything on a Hubble diagram, and then you look at the residuals, the Hubble residuals, versus the mass of the host galaxy, there's this small 4-ish sigma correlation, basically, between the Hubble residual and the mass of the host galaxy. And no one has any idea why this is. The thinking is that it has something to do maybe with the age of the galaxy, and the age is tied to the progenitor, so we're seeing some very small effect. But there's no good story. And what I do with the Pantheon analysis is look at if this changes with redshift, and it seems to be disappearing with redshift, which has matched some predictions that this is tied to the age of galaxies, because galaxies' ages are changing as you're probing to higher redshifts. So it's generally pretty messy right now and confusing. And this isn't the biggest effect, but it's big enough that it scares us. So what was found in the DES sample is that if we make a correlation plot of the size of this host mass step, basically kind of how big this little jump is, versus how much scatter is in our supernova sample.
Just before you move from there, there is a mass metallicity relation.
Right.
So why do you say it's the stellar mass and not the metallicity that correlates?
Yeah, so we try metallicity also, and it's like a little bit weaker than the mass, but it's very close. So like, yeah, this is 4 sigma, and metallicity is like 3.6 sigma or something. So yeah, it's hard to know which one it is.
Metallicity makes more sense from the
physics
point of view.
Right. So
why would the stellar mass matter for the single object?
Yeah, for some reason, kind of sample to sample, mass has had the highest significance, but it's always.
Makes no sense.
I agree. It's just what we found, but there's not a kind of key thing. Or
well, I would disagree with that. I mean, yes, mass ties you back to age, and age ties you back to the Laplacian distribution. Which, if you have more than one type of progenitor, as you go back, as you go forward in redshift, you're going back in time. You're just looking at the Quantum supernova.
Yeah.
Right? In which
Yeah.
case sampling, you might be sampling either the same type of population or two populations at the same development point.
Yeah.
At which point you can tie back into the sampling.
Yeah.
But if you're saying it's a matter of age, then there should be evolution also with redshift, right?
Right. So we are seeing it's just low significance. We just don't have a big enough sample to see it, but it does seem to be going away roughly with redshift. Yeah.
Is there a trend with specific star formation, right?
Yes, that too. So that's also kind of similar size as metallicity. They're all around 3.5 to 4 sigma, but nothing's clearer than the other one.
But the problem is that all of these also connected.
Yeah, right.
Yeah, no, they're all correlated, right? But I think that when we talk about stellar mass, the biggest effect in stellar mass is that you're changing the specific star formation rate. That's the easiest way to.
Yeah. Yeah, right. Sorry. Yeah.
Some drift in the population.
Yeah.
And you've
Right.
already pulled in the Phillips relation.
Yes, we've already
They do
done
this.
it. That's
Here's an app.
yes, that's right. Yeah, and right. Yeah, the decline rate correlates with stellar mass, and so right. Yeah, there's a lot of kind of things baked in already. So I'm unclear what's driving it. So the new kind of piece of the puzzle is that we could fit this step for various samples, and then we compare that to how much scatter, kind of residual scatter there is of these samples. And for some reason that also we don't understand, this seems to correlate very well. So for samples that have higher scatter, they have a bigger mass step. And for DES, which is kind of the newest kid on the block, has the smallest amount of scatter, it does not see a mass step. It's the first survey to not see it. So something, well, we have no idea what's going on. Something is clearly sample dependent. I did this sample, and this sample, and I don't think I'm doing anything that differently, as far as I can tell. Something about DS, there's some sample dependence that's in here that we don't understand. But what I'm optimistic about when we start getting to the bigger DS sample or LSST is that you can start there's so much statistics that you can play with various sample demographics and try to figure out what's happening. Yeah.
Just with one clarity, is that intrinsic scatter of distance or
Distance
distance?
modulus. Yeah. So it's the after measurement uncertainty is the leftover distance modulus scatter. So it's
So this is not the level that you actually measure. This is not your actual residuals level. This is your residuals after you deconvolve the part that you think comes from observational.
yeah. So or to put it a different way, if we want our reduced chi-squared to be 1, with measurement uncertainties to be much greater than 1, this is the yeah.
Why did you, if you go back one slide?
Yeah.
Why do you call it a step? I understand I can sort of see a step, but one
Yeah.
is a slope.
So in kind of my latest analysis, it looks a bit slopey. In a bunch of other analyses, there's been very detailed analyses saying a step fits the data much better than a slope. I mean the step. I think some people like the step idea more because it gets at some kind of binary progenitor or something. So you're either this or you're this, and that's what a step gives you. But this all just feels weird. I mean,
One thing I don't understand is this is a 4 sigma result.
Yeah.
Then you have 2 New York Times articles and a big fuss about the Hubble constant deviating by 3.5 sigma.
Yeah.
So you're regarding 4 sigma as, oh yeah, maybe it's not real. And then the 3.5 sigma in the Hubble constant is something real.
Yeah.
So
okay.
I don't understand that.
Okay, so no, this for what we're doing is real. I'm not. Yeah, it's real. We have no clue what's going on. And for the Hubble constant tension, I'll talk a little bit about that in 20 minutes. But we put in this correction, and then we also try to correct for specific star formation and all those other kinds of things. But just to give you a sense of scale, this step is 0.045 mag, whereas the Hubble constant tension is 0.2 mag. And what really matters for the Hubble constant is what's your demographic difference between your Hubble flow sample and your calibrator sample. So as long as the demographics are roughly even or close to even, this 0.044 will go down to 0.01. So that's still 20 times smaller than the Hubble constant tension. So I think it's I don't know if embarrassing is the right word to use, but it's clearly something we have no clue what's going on. Something's pointing at some physics. We need to understand it. It's not the thing to kill the Hubble constant tension, but what I was saying before is W is way harder than H naught, I think. So, and this will hurt W. Okay. All right, so I guess, oh yeah, I think I'm at the hour. I'll talk more about HST in the next one, and let me just, okay. Basically, I was going to talk about just what's going to be interesting with residuals and measuring sigma 8 from peculiar velocities or magnification. And then I was going to say a quick word on W first, and that basically my team is working on optimizing that strategy. And then I'll just kind of leave it here for a final thought. So I think what's so exciting if we can do things right is that our biggest sample today has 1,000 supernovae. In 5 years, we'll have 1,000 supernovae every 3 days, which is just amazing. And kind of what happens in the next year? Well, kind of on the H0 side, you'll have these new ACPOL results hopefully soon, and we're going to have a new SHOES result. I think maybe this summerish. And if this foundation supernova redshift sample, we just keep getting bigger. DS will have its new W result, which should be, I think, the most precise W measurement. Kind of on the GW side, there's potential to measure H0 from that with standard sirens. I really think in the next year, all the H0 stuff, it's either going to be confirmed or something crazy is going to happen. But there's two main things going on right now that 4 sigma tension is either going to become 5+ sigma tension, or someone will find something. But I bet on the former over the latter. So I'll talk about that in the next talk, and happy to take any more questions. Thank you, everybody.